I believe this is the sampling theorem. Is it not? I believe that's not. We are recording.
And the T in this
Oh, no, I can't see
based off of omega s.
Say again, sorry.
T in this equation is based off of our omega s.
Yes, it's like the sampling period. So it's not 1 over omega s, it's 1 over f. So you have to take omega out of 2 pi into hertz and then 1 over that. Okay, feel good about that? Okay, so now let's imagine what the sampled spectrum of this is going to look like. I'm just going to draw it below right here. Okay, I'll give you the easy one. We're going to have a triangle right at 0. That's the value of n equals 0, right? What is this amplitude?
It's 2.
So we got pi halves divided by pi fourths, which is indeed 2. Great job. Feel good? Feel good about that? Anybody have any questions?
You can also multiply by fs. Wait, hold on. 1 over t. Never mind, just keep going.
Okay. So the amplitude is 2 because it's 1 over t times the amplitude it was, which was pi halves. Okay. Now these tick marks are going to be at exactly the same place, right? -4 and 4. Remember, this is omega still. Okay. Where do we draw our next triangle? Let's say we'll do this one.
I think you just start right over. You know, it's basically border the thing. So you go 4 to 12.
Is it divided by 1?
It is going to go from 4 to 12. It's going to be centered at Nyquist, which is right. So we'll put our point right here. We'll draw it back 4 and forward. So it's going to be -4, just like I said. Or it's going to be 4, 8.
Yes.
Yes.
1 over t pi over 4 times pi halves would give you pi squared over 8.
1 over t. Oh yeah. Wait.
You do fs times
1 over t is pi over 4
True.
times amplitude pi over 2.
That is interesting. So we're gonna get pi fourths. Oh no. Oh yeah.
I did the math wrong.
Oh wait, 1 over t is
Oh, 1 over 2 equals f.
1 over t equals fs.
right.
Okay.
So
You're
we're
right.
good.
Still 2.
What did we say? What are we sampling this at? The Nyquist? So
Yes, we're sampling at Nyquist. Can anybody tell me if you were just looking at this, could you tell that we were sampling it at Nyquist?
Yes.
How?
They're touching each other.
Yes. Just barely, right? Like they're just barely touching each other, so you're not getting that overlapping, which causes the signal to be aliased and information to be lost. Okay. So say again.
If you're sampling over Nyquist, it's going to be farther apart equal to 1 over 2. Over, it's going to be overlapping.
Yes, in theory. Sometimes you get lucky. I remember from a homework assignment, you had a signal that was like
I see.
centered out over here. You can sample it under Nyquist and the triangles happen to go in between each other. So you got lucky. That happens sometimes, but if you have a signal that's centered at 0 like this, then yeah, you're right. Yes.
Sorry, I think it's a little bit late. So how did we get our amplitude to be 2? If our sampling frequency is 8? Shouldn't it be like T?
So our original amplitude is pi halves. And so we times that by 1 over t,
It's less than the same.
which is pi halves times fs, which is omega s over 2 pi, and omega s is 8.
Oh, I see. Okay.
Does that make sense?
Yeah, it makes sense.
Okay. So we're gonna get our copies. They're all gonna be at amplitude 2, and they're all gonna be touching just barely at the edges. We haven't lost our signal. That's fantastic. Okay, now let's answer the third part of Dr. Harrison's problem here. What's the ideal low pass filter we need to reconstruct our original signal?
When you put a rect centered at 0 with, I think it's a height of 2 still, although I could be wrong on that part, and then it goes to -4 and 4. Because then you're effectively just taking one sample of the signal and you're not taking the rest of it.
You can see how if we included more than one triangle, in theory, that's a different signal. All right, so we only want one copy. That's right. Now, you're not quite right about the amplitude. If you're exactly recreating the original signal, what do we want to do?
Have one, amplitude of one.
Close, but not quite.
You want an amplitude of 1/2, because you want to get rid of the 2 there. You want to multiply it by something. Like,
So our goal is to take the amplitude back from 2 to pi halves. Because that's what the original signal amplitude was. We want to duplicate that exactly. So what do we multiply 2 by in order to get pi halves?
See? Four. Yeah, pi 4.
Yep. So our amplitude should be pi 4. Feeling good? Okay. If I had done this yesterday, it might have been helpful to some of you who hadn't done homework 12. Sorry. But yes.
Can you briefly explain that, what you just did?
Yeah, of course. So in theory, we want an ideal low pass filter that's going to give us our original signal. Right? And we have this. And so we want a rect from -4 to 4 to delete all the copies this way and that way. But we also want to rescale our amplitude back to the original signal amplitude. And so what do we have to multiply 2 by in order to get pi halves? It's that's right. That feel good? Feel good about that?
What is the equation of that rect function?
Good question. I believe your default rect is gonna go from -1/2 to 1/2, correct?
Yeah.
I have a page number.
You have a page number.
Yeah, it's page 6.
He asked.
689 and.
Page 689, I hear is a good page for the formula of that rect.
Which one?
I'm pretty sure it's gonna be like rect of omega over 2 times 4. My guess, probably times by pi fourths.
Did they ask for a definite correct or triangle?
Somebody was asking for the formula of this rect, but triangles is also useful.
That was triangle. That was
Okay, I'll still write it though. Still a nice page.
the one for the rect is like the.
Okay, we have answered the Dr. Harrison problem. How do we feel?
Yeah.
We feel good? Thumbs all around? Great.
You could just outline for the recording where you started and like you don't have to like go through the whole thing for them, but you
Okay.
can kind of point out, this is step 1, this is step 2.
We started here with the formula. We put it in the form where we could transform it into the table by figuring out what capital W was. And then multiplying by 1 in order to get the W over 2 pi. We transformed it. We graphed just the Fourier transform. We then figured out what TS and omega S would be by determining the Nyquist frequency at 2 times 4, right? Twice our highest signal. Then we sampled it using this theorem. We got this graph, which is X bar of omega. And then we figured out our ideal low pass filter to reconstruct the signal, which gives us an amplitude that multiplies by 2 to give us our original amplitude and cuts off all of the other samples in the spectrum. Okay, hopefully that's a good quick summary of that. Now I have a fun little question for y'all. Imagine that I wanted a DTFT of the original signal, and we were given like some Fourier. We were given the continuous time version, and we sampled it at Nyquist. What does the DTFT of this signal look like? I'll give you a really quick hint. It'll look a lot like this. A lot. There's in fact, yeah, go ahead.
Take the x-axis and then divide by frequency.
divide by your sampling frequency. So we've got copies here every 8, right? So let me see. So if I divide this by Fs, and we're dividing by Fs, not omega s, that's an important statement. What tick mark does this peak get centered at? 2 pi. Right, and if y'all remember, the DTFT is 2 pi periodic, always, always, always. If you see something that's not 2 pi periodic, you don't see a DTFT. So if you scale everything here by Fs, what you're gonna get is the same amplitude, of course. But you'll get 2 pi right here. What tick mark will this be at? This will be at pi. Or you could think of this as capital W divided by Fs, right? Which might be more useful for you in different problems when you don't have like easy symmetry to give you pi. So on, so forth. Does that feel okay? I saw a question back there and then we'll go over there and forward. Yes,
So how come the amplitude isn't scaled as well?
good question. We already scaled the amplitude by using the sampling theorem. You can kind of see that the sampling theorem is a really good analog to the just without this axis scaling. I'll get to you in a bit, Caleb.
Wasn't I got even radian second. And that, but it's like the Nyquist frequency, it's in hertz.
Yes, so this Fs is in hertz, omega is in radians per hertz. You can kind of see how at the end here, we're just left with like radians. Right, and so we've taken the frequency almost out of the axis. It's just scaled so it repeats every 2 pi. I believe you were next.
Yeah, just kind of the same question, like, what's the difference between Fs and F?
And F.
Yeah. The way you want to decide. 1/time period is equals to F, right? Which is equals to omega.
Yes, so you can think of this omega s as the radial frequency per second. F of s is like your linear units, you're back just to plain hertz, and typically your period is given in terms of hertz. So if you see t, it's going to be 1 over fs and vice versa. And if you're given omega s, it'll just be 2 pi times f.
So like the S is just a.
S just means sampled.
Okay.
Sorry. Yeah, you're good. I think Ryan was next and then I'll go back there.
I just had more of a comment, but with the omega thing, I saw in the book that they're saying that omega is like a sample, or sorry, big omega is like a sample lowercase omega. So they had a formula of like omega, big omega equals little omega times the period. That's where you can do all that stuff where you like convert it or whatever.
Exactly.
I'm making that comment for the.
Dividing by fs is the same as multiplying by the period. That's a great connection. Okay, yes.
Can you explain the difference again between these bottom two graphs we have? So the top one is taking a continuous time function and we sample. And the bottom one is, what is that one? Discrete time?
This is in discrete time, yeah. So in the sense, this is like a discrete sampled version of the continuous Fourier transform. This is as if we did the DTFT of the discrete version of the continuous formula that we had at the very beginning.
Okay, I mean, that's sampled at every whole.
So this is at every copy of the sampling frequency in omega s. And this one is just scaled, so the copies are every 2 pi. Also, I'm sorry, I just get sweaty when I'm nervous. So it's okay. Don't be alarmed for my physical health. That's all I'm saying. Okay, yes, Ryan.
I guess a follow-up question, but that sampling theorem, is it like the same thing for the DTFT or?
Don't do that.
They're very close. Does anybody have the definition of the DTFT? somewhere easily accessible? Cause I don't have it memorized either. I'm sorry, it's not professional. But we can look it up.
I don't know. So we get you. I'm pretty sure I have the truth. No, I forgot.
Gonna be okay, guys. That'll be all right. Yes. Pretty good.
Questions, right?
That's.
I take it again, man.
But yeah, it's pretty good. Yeah, we can talk about how that's kind of the.
But we say there's a better one that I can say.
No, it's all right. I probably won't like discuss this in terms of the original formula for the DTFT, but y'all, I want to emphasize this as a possible method for you to calculate DTFTs relatively quickly. Given a function, find the Fourier transform of that function, sample it every omega s and scale it by 1 over TS, and then shift your axes so your copies are every 2 pi. That's a very feasible method for you to do a DTFT relatively quickly without some hard math calculations going through the formulas. Yes.
I have some formula.
I would love a formula.
It is, x of capital omega is equal to, the summation from n is equal to negative infinity to infinity of x of n times e to the negative j capital omega n.
Oh, okay, I was right. Cool.
So basically, it's the Z transform evaluated at,
This is the wrong omega.
yeah, and the one I put in here, I put inside the square brackets E to the omega. But I think it's just simpler notations for the capital omega.
Makes sense. Yes.
It will always be the sampling. Divided by pi. If it's centered on the x-axis or the y-axis.
If you're scaling it to get the DTFT, you'll just always divide by the sampling frequency. You can think of it as in the sampling theorem version, you're gonna have a copy every omega s. In DTFT, you're gonna have a copy every 2 pi. The way you get there is by dividing by omega s. I don't know which one of you first. I'll go with Jack.
So say like on the final, they ask us to do a problem with like a DTFT. Would you recommend doing this and then like scaling the x-axis by the sampling rate and everything like that?
For me, this is for me. I am not you. This is the easiest method for me, visually in my head. But again, you are not me. There are other methods you might have that are easier or make more sense to you. If there are those, do those instead. Yes.
Can we do this second method really fast? Because
You want to do this?
sure.
We're going through the, okay.
So that we have both ways.
Yeah.
Everyone just want to veto that?
No.
Yeah, no.
You want to do one of those?
Okay, let's veto it.
Let's talk back there.
Yeah, really quick. Can you just quickly go over how you found the bandwidth?
The bandwidth?
Yeah, like kind of the hoops you go through to change the C squared into a form that you can see.
Oh, yeah, sure. So, here we saw the interior of this was 2T.
The quiz.
And our goal was to make 2T look like capital W T over 2. Because this is format that was given to us in the table. Okay. So we basically multiplied it by 2 over 2 to give us 4 T over 2. They're pretty good.
In the table, sync squared has.
Exactly. And the W there is just a constant meaning width. It's not related to all of the different W's and omegas we have over the whole class. It's just they chose a stupid letter because I don't know. Okay. Whoa, we want to do one of these, you're telling me? Yeah.
No.
We don't? Okay. That's fine by me. I can maybe film me doing one of these later and send it out to YouTube. Would that be good?
Yep.
Okay. All the terrible summation stuff there.
Thank you.
I'll go up here and then there.
Really quick, can we even do that with that X?
So this is going straight from a discrete version, and you can kind of see that that's a continuous time function that goes. So you could think if this was sampled at some frequency, you could get an X of n. And then we could then go straight to the DTFT, but it's not very fun. Yes.
I understand like how you kind of are like brain, but like if you were able to do like you just said like a video doing a problem, that'd be cool because we could go back and like forward.
You can go forward, backward. Okay, so I'm gonna say DTFT summation process. That's what we want in that video. That would be good for everybody.
That or like any homework problems you do.
I don't want to do all the homework. But I'll do a few maybe. I'll do a few. But at least this. Okay. How do we feel about this? Are we okay moving to another subject?
Yeah.
Yeah, we're good. Okay. Which of these ones do we want to do next?
That's a question.
Sure.
Are you gonna not do 4-year series because you didn't cover it last year and it might not be your best topic?
Yeah, I don't really want to talk about Fourier series. I don't know if it's on the test. I kind of assume it's not.
It's a quiz question though.
It was a quiz question. That's a good point. Okay.
You don't have to do it if the last.
Seriously. If I put that in the video and not do it right now.
Yeah.
Okay. Again, which one of these do we want to do?
Zeros.
All zeros. Ooh, sounds fun. Continuous or discrete? We'll do both.
Yeah.
Just kidding. Imagine I only give you one.
Yeah.
People would be unhappy with.
I love.
Not too much. Not too much. Checks. Okay, let me give you a pole zero plot. Let's see. I'm feeling a pole right there. Pole right there. I'm thinking a zero all the way over here and a zero all the way over there. That's been fun. Seems like a good time. Sure. Okay. I can make it work. It's symmetrical. It's nice. I'm complaining. Yes.
Just throw in one that's not a conjugate pair.
But I wanted them to be conjugate pairs so I could show you something.
Okay, okay.
But I could.
You don't have to.
I'll do it in a bit. Okay, do we continuous or discrete first? What do we want?
Continuous.
Discrete, okay.
No.
That's no?
Continuous first.
Add on to the discrete.
Okay. I think discrete is a little bit harder, but we'll do continuous first. Just to give you we'll sneak peek. Hey, everybody, what is this beautiful axis?
J omega.
J omega. Love it. That's the Fourier. So in values of omega, what is that point right there? 0. That's omega equals 0. And say omega equals 4 is down here. Or -4 is down there. And then omega equals 4 is up there. You can see how this axis is just like a slider that we can adjust by changing values of omega, right? And you can see how, like when we're doing our magnitude and phase plots, omega is our axis. And so when we're going from negative omega something to positive omega something, we're just moving along that axis. Okay. Let's say that these pole zeros are given to us by our transfer function h of omega. This is just sort of the theory behind these pole zero plots. It'll be super quick. H of omega, let's say it has a numerator, f of omega, over g of omega. G of omega is just our denominator. And you can see how this is equal to the magnitude of f over the magnitude of G. And these are functions of omega, like they could change with omega. I just got lazy. And the phase of F over the phase of G. So you can think the magnitude of H is equal to the magnitude of F over the magnitude of G. And the phase of H is equal to, and a little bit of complex properties here, the phase of something divided by the phase of another thing is equal to the phase of that minus the phase of the denominator. We're fine with that? Okay, great.
Write that out.
It's arctangent math.
It's just the whole phase thing.
Think of it as like this. E to the j pi over e to the j pi halves is equal to e to the j pi times e to the negative j pi halves. You can see how pi minus pi halves is going to be the multiple of those. Feel good? Okay. So these two functions are what is going to give us our pole zero magnitude and phase plots. So let's start at omega equals 0 because I think that's the easiest point so far, and we're going to draw lines to each of our zeros and each of our poles. Now you're going to notice something interesting when we're doing this in continuous time, but we'll once we get there. We're going to think, what's the magnitude of each of these lines? I'll call this magnitude D01, as in the distance to the first zero. So this one D02. This one D pole 1 and D pole 2. Okay, our magnitude from that equation down there is going to be equal to D01 times D02 times D pole 1 times D pole 2. How does that feel? Make sense? Now you're going to notice a fun fact about this function that we chose. Because they're symmetric, wherever we put this point on the omega axis, this distance is always going to be the same as this distance. Imagine I drew them well. So they're symmetric. Okay, I'm telling you. This distance will be the same as this distance, and this distance will be the same as this distance. What does that tell us about the magnitude?
You need a flat line.
You always won. That's just a neat property of this pole zero plot that happened to be the case.
Is that true for every pole zero plot? Or
It is not.
Yeah.
Let me say this pole was right here. That is not going to be true anymore, right? We are no longer comfortable. Even if both of these poles were over here, that wouldn't be true. It was just a very lucky case that gave us 1 for all values of omega.
That's symmetry across j omega.
And again, this is also in continuous time. It'll be a little different when we go to discrete, but we'll cross that bridge when we get to it. I'm going to move this pole back over here because I like it better over there. Okay.
Gotta be a little lower.
Oh, my bad, everybody. That's my mistake. What about right there? Are we happy? Perfect. I can draw it again. You want to spend time?
You're fine.
Okay. All right. This is D pole 2. So if we're thinking just about the magnitude of the lines for magnitude, what are we going to do for phase? The question. Angles. Yes, very good. We're going to be measuring from the real axis this way, as we're used to doing with angles. And we'll see, okay, what's this angle theta? We'll call that theta 01. What's this angle? Theta 02. And here, signs matter. So when we were doing magnitudes, it was always going to be positive. We're just looking at the length of lines, right? But now phase is where the direction above or below the axis, that's where it comes in. That's where we store that information. So say that this angle theta 01 was, say, pi 6. Theta 02 is equal to negative pi 6. Do we feel comfortable with that? Feel good? Great. And then we'll measure an angle all the way to D pole 1. So call that 5 pi 6. And then we'll measure all the way from the real axis to theta pole 2, which is going to be negative 5 pi 6.
Right?
Yes.
How do we, okay, so first of all, the angles are always measured from the point on the j omega axis, correct?
Yep. So if you were down here, you'd be measuring from that.
Gotcha, okay.
So in theory, like this would be theta 0, I believe we called this 0.2. That would be theta 0.2 if our omega was, say, negative 6. Feel comfortable? Yes.
Like, it could be wrong, but it does say to measure the angles at the poles and zeros.
Oh, does it do from the poles and zeros?
For continuous time or?
For sure, continuous. I think both though.
Okay, I believe this is going to give you the same results. It's just a sign. And we'll talk about some wraparound properties that will get us there as well, but yes.
Is it true, like, so when we're doing this, do they want us to always just put it in the positive angle version instead of putting them like instead of negative pi over 6 or whatever, find like the positive version of that angle, nothing? It doesn't really matter at all.
So you can graph your phase as being from 0 to 2 pi or negative pi to pi. It really just depends on what you're asked for. I prefer negative pi to pi because that feels clearer to me phase wise. And so you'll get those plots that are like from 0 degrees to 180 up here and negative 180 down here. And you can kind of see how in theory, if you just shift this up there, it's like 0 to 360. Okay. Somebody had a question over there.
Yes, same question. So we're always, well, not always, but by default, you just go from negative pi to pi.
That's what I like to do. Yeah, Stefan?
Also, I feel like whenever I do the math for it, having pi over 6 and negative pi over 6 or, conjugates like that helps a lot with Eulers. It just is easier to see.
It is nice with conjugates. By the way, you can probably tell what the phase at 0 is going to be. What's the value? 0, because we're going to have theta 0.1 plus theta 0.2 minus, this minus is coming from the poles being in the denominator, right? That math over there. And then we're going to do theta pole 1 plus theta pole. Yes. So phase of H, we'll say omega in theory. Right now, it's evaluating omega equals 0. But again, you can do this here. You can do this here. You can do it all along this axis to get you your phase plot. I believe you were first, and then I'll go over there.
Well, like, why are we not calling theta 0.2 negative down? Does that
Theta 0.2 is negative. Sorry, I don't know if this minus sign is clear.
okay?
Yeah,
Okay.
it is negative, and that's important. Yeah.
Do we need to make sure that the angles always range from negative pi?
Like the measurements you're making?
Yeah, on the poles, like I could see like an angle coming, sweeping down like this, and it would come down to pi, go up like above pi, or do we swap it to a negative angle?
Good question. You can do either. I just picked one because I think it's clearer to always do one. But in theory, you can measure this as negative pi 6, or right, you could measure that as what is that, 11? Like
What the math?
11 pi 6? The math will work out to be the same as long as you remember that the phase wraps around, right? We're never going to get more than 360 degrees of phase. Like that doesn't really make sense. It's just you have another cycle, right? And so you just go pi 4s.
Phase always is,
It's always some value in between these two lines.
sure.
So if you go up to 180, you're not going to plot a point that says like 190 degrees. You'll just come up here Plot it right there. Does that make sense?
Versus needs to be between 180 and negative 180.
Yep. Or 0 and 2 pi. Whatever your convention is, whatever makes more sense to you, graph it that way. But it's going to be within that 2 pi bounding box.
That way we see like whenever we I think we had a fit slowing around. So then you would graph that, you would put the vertical line down and then keep going.
Exactly. That's a lot of your phase plots do that. Because in theory, a computer's like, wait, I have to draw the line between the points, guys. So point there and there. You know, it needs a vertical line. That's what's happening. So, okay. Does that make sense? Really good. So, as you'll be moving your point of omega, you'll measure the thetas of your zeros, and you'll subtract the thetas of your poles. That makes sense. Do we feel good about that? Now, I'm going to give you a lovely property. Here's where those conjugates come in, everybody. Because these are all complex conjugates, what does that mean about our original, like, h of t? What does it mean? Give us some information. I heard real. That is correct. And listen to me when I say this. When you have that property, when all of your poles and zeros are complex conjugates or only on the real axis, you have a beautiful property. And the beautiful property is your magnitude plots, h of omega, will always be even. What does even mean? Anybody, tell me what even means.
X of t equals x of negative t.
Exactly. So we can write it that way. Somebody said I'm symmetric about the y-axis. Both are right. So if we know what's happening over here, we know the same thing is happening. Okay, that drawing was the same thing is happening over here. And that's exactly symmetric.
Complex conjugate is symmetric across real axis. So the top one.
You can say they have the same x value and their y values are negatives of each other. Yep. That's what a complex conjugate is. So if you see this symbol, that means conjugate. Yeah.
You just say that in English again?
Yeah, sorry.
You said big complex.
You can think of it as, you see we have two poles there that are conjugates of each other. Let's say that the poles are at we're in continuous time. So let's say that's S. I'm going to say that they're at -1 and -1j because that's easiest, even though that's not what the plot says. So S -1 minus j. And then what's the conjugate of that?
-1 plus j.
That's right, -1 plus j. You reverse the sign of the imaginary. That's what a conjugate is. So let's FOIL this out and see what happens. We're gonna have s squared, right? That's our easy term. And then we're gonna have s times -1, so negative s. We're gonna have s times j. And then we're gonna go the other way, s times -1 minus s. And then we're gonna have s times negative j minus sj. What is notable about this? The imaginary parts cancel out and they are gone. So we have s squared minus 2s. And these sj's cancel out. Nothing imaginary there. That's why complex conjugates result in real functions. And now they have to be either both poles or both zeros, right? Like if, say, this one was a 0 and this one's a pole, those aren't going to be multiplied by each other to cancel out, right? That doesn't make this real. They have to be the same type. So either they're both on the numerator or they're both on the denominator.
All poles and
all of them. Yep. It's kind of like imagine imaginary parts are like serial killers. If there's even one inside your house, that's bad. You want all of them gone. Full example. Somebody else had a question. That was it, yes.
So like, what would be the stability? How do we know stability of these systems?
Stability, good question. Okay. Okay, if you had to guess which one of these were important, zeros or poles for stability, which ones matter? Poles, why poles?
They can make things go to infinity.
Yes, they destroy your function, right? Whatever happens in the numerator doesn't really matter, you know, it's the denominator that breaks your math, right? And so you need all of your poles be in the left half plane. This is the negative half you can think of in that essence, right? This essentially means that whatever your original Laplace transform, it converges. You can think like you can do an integral, you can figure out the area under e to the negative s as it goes to infinity, right? But you can't do e to the s. It's just gonna blow up and you're gonna be in trouble. That's summary, left half plane, that's where you want your poles.
What about in discrete time?
Discrete time, good question, we're gonna go there soon.
Outside the inner circle.
Yes.
I got it.
Yeah.
One more thing from continuous time was I remember we also talked about the rock, and you can do something with that for pole zero plots. How does that work again?
Like figuring out if the rock is stable. You can think. What were you saying?
I remember there was a question where like we had to look at a pole zero plot and figure out where the region of convergence was from that.
Oh, good question.
Yeah.
Okay. Okay, I'm gonna erase this. If you really are attached to it, too bad. Sucks for you. Okay. Let me just put some poles up here and you're gonna tell me whether it's stable and where its rock is.
Can't you choose the rock to make it stable?
Not with Bibo stability. Like in this, like I guess in theory you can choose your rock to be specific area, and I won't spoil that so you guys can answer this. But if we are looking at causal functions, is this a stable function?
No.
Why not?
As one of the right.
That's right. It's over here in this plane. What is your rock if this is a causal function? S is greater than 3, right? So it's going to be right of your rightmost pole if we're using causal functions. Anti-causal is the opposite. It will be left of your leftmost pole. That's not as important to remember as the causal one. Remember causal. Your rock is right of your rightmost pole. Yes.
So you were talking about stability over here with poles and left axis. How does that relate to what we just talked about with the rock?
How does that relate to region of convergence?
Yeah. Like what was your point here?
So my point with there is like Bibo stability. Right? If you put in a bounded input, you'll always get a bounded output. If your poles are in the left half plane. That's not guaranteed here. I could go into a deeper example than that, but I think that might not be super worth our time. I just want to give like a super fast trick. But you were saying, sorry?
Yeah, just following up. So the Bible stability, if it's causal. So if you use the causal region of convergence, that's Bible stable. Is that what you're saying?
Yeah.
Okay.
And you're probably going to be assuming causal if you're asked about Bibo stability. Is test. If I'm wrong, you can slap me. This once and not very hard. Okay, yes.
So this only is for Laplace right now, right? What
We're doing continuous time.
Is this true? Okay, so yeah, so like blanket continuous time. No, Z is discrete. Z is discrete. That's
Yeah, we'll go to discrete in just a second. Yeah, Ryan.
Just a clarification with the region of convergence, we're saying that the real part of S is.
Yeah, real part of S. That's a good say because in theory it doesn't really matter what your Y value is.
Oh, okay.
Right? Because
The effect on.
it's as long as your X part is greater than that cutoff,
Okay.
which is the real part. Somebody was over there, yeah.
Yeah, what plane is this again?
This, I believe, is the S plane. Good question. Yeah, so that axis is J omega. Okay. Which one is J omega? It's the Y. Yes, Stefan.
So going back, we now have magnitude, we have phase.
Yes.
We're gonna be asked to then factor back into just H of W, like we know magnitude. Is this only just to like find the magnitude and phase plots?
That's pretty much what I was guess is gonna be happening. I don't think it's likely you're gonna be given a magnitude and phase plot and then reconstruct the entire original plot. But in theory, if you were given a magnitude and phase plot, say, let's say you had a pole right there and a zero right there on your J omega axis. Theory, if you were drawing your phase plot, what would that look like? Anybody tell me? We had a pole right there on the negative part, the omega axis, and a zero right here. So we're gonna have an infinite, we're gonna have like a discontinuity right here. And then it's gonna come back down. And then right here, it's gonna be zero. And then it will go back up again. Does that kind of make sense?
For phase or for magnitude?
This is magnitude.
Oh, that makes sense.
Yeah, we're thinking magnitude.
That makes sense.
And so you can kind of see, hey, when I have big peaks, I'm probably pretty close to a pole. When I have minimums, probably close to a zero. Those are some little clues that maybe will help you. And if you have like full discontinuities, and if you have zero, you know you hit one right on the mark. Yeah.
When we say that the Laplace transform, the rightmost part gives us like the causal region of convergence, does that mean that it gives us it inverts into a causal system?
Yep. Because in theory, there are different regions of convergence for different types of functions, like the anti-causal with the negative step functions that are flipped. Remember the causal ones, I think, is most important for you.
And causal system just means you plug in a causal input, you get a causal output, right?
Pretty much.
Nothing with the past.
So when we're talking about these at pole and zero this group, if we were to line off to infinity, would we converge at one when it does that in magnitude?
In magnitude. No. You can think of one right here at zero, if these were equidistant. That's when your magnitude is one. Does that make sense? In theory, because your distance to your pole is zero, it's like dividing by zero. That's the sound when things blow up. Yes.
So kind of like as a resting position as you go to infinity or to negative infinity, as long as you have both poles and zeros, it's basically an approach one because.
Oh, yes. Was that your question?
That's what I said,
Yeah. If you had like, if you had a zero and a pole right there, it would be like a 0/0 type of situation. Then you'd L'Hopital it, you know?
No, sorry. Okay, my question is, you would go like, say we're up.
Yeah. So as you're going to infinity, the distances to this zero and the distances to this pole basically look the same. It's like if you have infinity plus 2, that's infinity. So it's 1, pretty much. You could L'Hopital it. But that's the premise. Okay. How do we feel about continuous time pole zero plots? We feel good? Hey, all of the stuff we just learned is pretty much the same with continuous time, except we're not doing it on this axis anymore. Right? We're gonna be doing the unit circle.
Even symmetry, or is it conjugate symmetry?
The guy in our study room that.
Okay.
Studying like in the PV room, we're next door, like. We're handling, we just hear one.
Speaker when they mean the test is.
Yeah, the unit circle lives right here.
Yes.
That's 2.
I was gonna use it.
This is self.
Okay. Now And you see how the unit circle is defined by e to the j omega. Does that make sense to everybody? We're comfortable with our Euler. Great. At omega equals 0, where are we on the unit circle?
Oh, at,
1. That's right. Leading to 0 is 1. That's a little shortcut if you guys like. And you can see how if we go to e to the j pi halves, that puts us right here. E to the j negative pi halves, right there. E to the j pi or e to the j negative pi, gonna put us right here. Can you see how if we go from omega equals 0 all the way through omega equals 2 pi, we've evaluated all values? 2 pi periodic DTFT, guys. Wow. That's so cool, right?
Yeah.
Gotta love it. Got it. You have to. It's legally required. Okay. So same thing we're gonna do as before. We're gonna trace lines to our zeros and our poles. And we're gonna evaluate, the magnitudes. So here, is our magnitude gonna be greater than or less than 1? This is just like a really fast way I like to do these magnitude plots without getting like a high level of detail and taking a long time. Is
Less than 1.
less than. Why is it less than?
Because the x's are really far away, and that's the bottom part. And then the zeros are really close, which is the top part.
Exactly. Numerator small, denominator big. So at 0, our entry right here is going to be less than 1. Now, what about when we're here? Less than, equal to, or greater than 1?
Equal to.
Equal to. Why?
Same length.
Because, it's symmetric between the poles and the zeros. They have the same magnitude. It's 1/1.
Great. So at pi halves, we're gonna have equal to 1 right there. Okay, super quick question. What about negative pi halves? Same thing. Why?
Because they're like conjugate pairs.
They're conjugates. If you forget that, you can also just measure it again. But if you don't forget that, hey, you just saved yourself a whole half of the graph. You don't have to graph. Isn't that nice? Okay. Then we're gonna come out here to pi and negative pi, which in theory will be the same value again, because it repeats. What about this one? Is this greater than or less than 1? Greater than. Why?
Poles.
Yes, numerator is much bigger than the poles. So you're gonna have a value that's up here.
Zeros.
How do we feel? Feel good? Yes.
See.
No. This, yeah. Let's call this is, I believe we're discrete now, right? So this is Z. Wait, no, that doesn't hold. This is the real part. This is the imaginary part. Feel good with that? Okay. Hey, was there another hand? I feel like there was. Okay, yeah.
Radians for the graph is.
Like
When you just put the dots on?
this one, yes. This is these axes. I'm sorry. This bar is omega. As we're changing values of e to the j omega, which I guess I erased. That is in radians. Again, you're gonna get copies every 2 pi, right? Okay. How do we feel? Yes.
What was the y-axis on that one?
Magnitude.
Magnitude.
It's a number. A lot of times you'll see them in dBs, means logarithms of number. Yeah.
Where to the basis number.
Get a simple magnitude. So have to multiply by B naught, right?
By B naught, you're saying?
Yeah, for.
Is there some reference to that in the textbook somewhere?
Yeah, in the textbook it says for the magnitude plot, we like multiply by B naught, but then in the homework we didn't do that because B naught was 0. We multiply by K. But they didn't talk about K in class, so.
So K is.
Okay. I think I have an idea for this. So,
It's just like a.
so let's say you have your pole 0 plot. I'm gonna make it really easy. Your poles are right here and you have a 0 right there. Okay, these are all at ones. This is -1, -1, and 1. So what is our transfer function? Can anybody tell me?
Yeah.
Yeah, Ryan?
Oh, also, is this discrete or continuous?
Let's say continuous.
Okay, so you'd have s plus one on the top.
So we're gonna have
S plus one on the top.
on the top?
Yeah, I was
Yes, you're
zeros. I figured that's
very good, Ryan. Very good.
have s plus j times s minus j.
Squared. We don't have a z squared.
Great. Now, is this definitely our transfer function?
It depends on if there's like multiplicity in your pole zeros.
Well, there's the multiplicity point, but there's another point that I think is also
We also have like a whole beat factor that influences it.
like in theory, this could be scaled by any constant, right? And we'd still have the same poles and zeros.
Yeah.
So that's what the homework was talking about with this K stuff. Or probably the B naught.
Yeah, I think those are the same. It's just
Just a different constant. So in theory, our transfer function is some scalar multiple of these poles and zeros.
It's just B naught is not the same as B zero. Cause like when I was doing it, I was thinking, oh, the B with the 0 on the bottom is gonna like, oh, if there's like a Z squared, A naught is 1. But then, oh, we only have one Z on the top, so that means that B naught is 0, but it's not B naught, it's like a different
Isa,
thing.
I think it's the coefficient for the highest order term.
Right.
That probably could be what it is. If you email me about this, I can talk about it in the video.
Okay, thanks.
Yeah, of course. And so can you see how if they gave you the value at some point, so h of -1 equals 2, you can figure out what k is? That's why in the homework you were given a condition like this, so you can evaluate and figure out what k is. Yeah, Jonathan.
So how does K apply to the magnitude and the phase response?
Good question. It scales it. Yeah, that's what people were talking about when you scale the axis by B naught. You can see how any number we calculate here is going to be correct for this section without that K. That makes sense? And once we know K, we know what that number is. Sure. I think you were first and then here.
So K with the S plane, is that constant also exist in both S and Z plane? On any magnitude?
Any pole 0 plot, you're gonna have some scalar multiple. And that scalar multiple is probably not 0, but anyway, yes.
Just for an example, can we put another pole on that graph just in the top right and it's off by 10 to the right side?
Okay, you want it over here by 10?
Sure, yeah.
Okay, pretty good. I don't need to draw all the sticks. Right there.
Yeah.
So you want a pole at
Like this is like not on the axis.
and it's not on the axis.
Not on the axis.
Okay, so that's going to be S minus 10 minus J.
Got it. All right.
So that's coordinate of that pole. Okay. And we get how that matches to that point. If you plug in 10 plus J, you'll put a 0 there.
Please explain.
Yeah, can you explain that?
So
Perfectly why I asked this.
so S is equal to some complex number, right? If that complex number is 10 plus J, we go over 10 and then up J, we're gonna cause a problem at that point, right? That's why we plotted the pole there. How does that feel? It's just a pole or a 0 can be both value on the real axis and the imaginary. Jonathan?
It might be easier if the complex number were put in parentheses so we could see as one single value, just like with a regular pole.
Yeah. You could say like S equals some real part plus imaginary part. If that imaginary part is 1, The real part is 10. That causes a problem right there. And if you flip signs, like if you wanted to put it right here, then this would be a plus J. Does that kind of make sense? Looking for eye contact and slight yeses. Okay. That's it.
I guess just go back a little bit. I just had a question about that K there. Does that really affect the face plot at all, or is it more just on the magnet?
The K does not affect the face plot. Why does the K not affect the face plot?
It's like.
These can only go from whatever to whatever.
Exactly. It's like if you're measuring from this point to this point, that's the same angle.
Okay.
Doesn't matter how far stretched out it is. Yeah. Yeah, you can go and then Plaid behind. What's your name, Plaid?
Jackson.
Good to meet you. Sorry, go ahead.
So you drew that X, fourth X over.
This one.
Is that why you put X equals 10 plus J?
Yes. The plus is because if you had a negative J value for S, hence the location of that would cancel out that part.
And it was negative for the.
Yes. So this one it's a minus if it's at a positive spot, because if I plug in a plus J, it will kill that. Exactly. Okay. Yes, that's right. Thank you.
Yeah, so for discrete time, going back to our unit circle.
Yes.
We do the phase interval. Like, let's say we're at pi force.
Okay, right here.
At that point.
Do you want to find the phase right here?
Yeah, do you just take it from that point? And so like that 0 that's right there, it would be a negative angle.
Yep.
Both would be negative.
Both would be negative. This one kind of the small value, this one bigger. And then this one, I believe if it was level, is also going to be slightly negative. Assuming that this line is above. So that will be your first value, and then this will be your next one.
Nice negative angles.
You can kind of see how this is going to result in a positive phase, because these are all negative angles and your zeros are relatively small negative angles. Your poles are relatively large negative angles. Because we subtract them, that's going to result in a positive phase. It's a little mind bendy. I know there are lots of sign flips. You can always plug it in and do the math. Always, whenever you want. Okay. Also, it might be nicer for you to estimate these in degrees. It sort of gives you an easier ability to estimate, angles instead of having to do pi halves, pi thirds, or pi sixths. It's like, it looks like 52 degrees to me, ballpark. That's just a personal Ryan tip. Yes.
So on that graph there, are those poles labeled at positive and negative 1? Right side over there.
Let's see.
On the other graph.
And this one? Yeah, these were plus and minus 1.
Wouldn't they be positive and minus J?
Oh yeah, minus 1J. This is like the J axis, the J omega. It's evaluated at 1. But yeah. Good question. Units are important. Yes.
They give us something like that and a million gold degrees and say what's the phasing.
Would they give you like a problem like that?
Yeah, but
possibly. I haven't seen the test. That's not an unreasonable question. Not a quiz. I think that's good probability then. Yeah.
So main takeaway, given a pole zero graph, you have an equation right there for phase and you have an equation right there for magnitude. Whenever it says what is the phase at W equals 60 or whatever, you put that there and you estimate the angles. That's how you use that equation up there.
Exactly.
Same thing for the magnitude. You just have to see where it is.
And in theory, if you were given a pole zero plot and then you had A through D and it's like, which of these are the correct magnitude and phase plots? Could you figure out how to figure out which one would be accurate? Right? Like they might have a peak at omega equal pi halves and you're like, would there be a peak there? And you could try it. You could actually look and tell. So this is a really nice system for evaluating magnitude and phase. If you forget everything else and the calculator has failed you, this is your fallback. Yes, Stefan.
So now doing the region of convergence and stability.
Oh, yes, I forgot about that.
So because the poles are outside the unit circle, it's unstable.
Correct.
In the region of convergence, that's where I need
It's outside.
Outside of your greatermost pole for causal functions. So your rock is all the way out here.
That's a radius from origin.
Yeah, it's a radial, it's like magnitude Z. Whereas in the S plane, you were concerned about the real part of S. In the Z plane, you're concerned about magnitudes. Is the Z magnitude greater than the outermost?
Yeah, going back to the in the S plane, I think I remember it was maybe even on the last midterm, it was asking like, when you had those three poles, two were in the negative and then one was the positive. Will it ever ask us about like a region of convergence in between those two poles?
Say things like, will it ever ask us about this? And my answer is, I don't know. Again, I cannot remember the final. My guess is probably not. Like, think about all of your homeworks. Were most of them concerned with causal functions? There were a few that were sort of like, oh, what about this anti-causal one? But those, in my opinion, were probably more like novelties. I would be more concerned with causal functions. That's where I would spend my time. If you have a bunch of extra time, which probably none of you do, you could spend it on making sure you're really comfortable with all these different types of rocks. But casual, causal, and anti-causal. Definitely not casual. I don't know. Maybe you guys feel like this is easy, but
Calling us filthy casuals.
no, y'all are well kept.
Yeah, eminent.
Okay, yes.
That W tells you where you're gonna look.
Say again. W meaning omega. Yeah. So your value of omega, either your capital omega in discrete land or your lowercase omega in continuous land, that's going to tell you where you are on the axis or where you are on the unit circle. Make sense?
No.
Okay. How do you feel about this? Do we want to talk more about anything? Do we want to move on to another topic? Move on. Okay, what do we want? Thinking whoever says something first.
Direct form 2.
Do you have 2 plots?
The direct form stuff.
Oh, yeah, do plots 1 and 2. We should do
Dude, that came up on the midterm.
After we thought it was.
There, let's do that.
Random like true or false. I was like, bro, this isn't bad.
What is this asking?
Put everything down, bro.
I wrote it down too.
Right.
I got very involved like
There is the limit.
There is the limit, and then out straight is the true. Yeah, pi is the limit.
Oh, okay. I probably will not draw over there that far. Okay,
Anything smaller than this.
makes sense.
I can write smaller though. I can write smaller.
Oh, it's all right. Thank you for being our recorder extraordinaire, by the way.
My best.
Ryan, as you talk about the direct form two, can you talk a little bit, having a special call for last one? You're asking like, why do we like, why did we got 1/0?
Bro, it was so weird.
Okay, I can talk to you about what I think the answer is. I didn't take the midterm. We could, some of you could show me it and I could talk about that too. But, okay, sorry, I'm a little flustered. Okay, somebody give me a transfer function. Yes.
Over 3 squared plus 2s
Plus 2s plus what? Oh, yeah. Somebody want a minus?
Yeah.
Wacky with it?
Yeah.
It's 2s. Okay, that sounds kind of fun. A little spicy.
Or this one would need.
Oh, that's right.
Spice it up.
Okay.
Is Ryan doing a good job, everybody?
Oh, shucks. No, I need to butter me up.
This one that good, great.
Okay, I'm just gonna start by drawing a whole bunch of blocks that we know are gonna be in this. That is not 1/8, this is 1/s. This is 1/s. Okay, so a lot of times we'll see 1/s blocks instead of S blocks. Does anybody know why that is?
Sadder.
Yes, we don't like noise. Integrators are better to noise than differentiators is pretty much the answer. I'm sure that's what you're gonna say, Jonathan. Okay, so how do we turn this into a system that's in 1/s instead of S squareds? How do I do that? Yes.
Separate the two functions, the denominator, the numerator.
Okay, so let's say h of s is equal to, is it y of s over x of s? So, so a lot of times people, what they'll do is they'll put the denominator over here. And move x of s back over there. Is that what you're saying?
Yeah, I just like to say 1/3 s squared minus 2s plus 2. And at the same time try to make the coefficient of the swing 1.
That is a very common system. So a lot of times what he's saying is by convention, we make this 3 here the leading denominator of the highest order term. The highest order term in the denominator. Sorry, my words are getting screwy. They like to make this 1 because it's a standard thing and it makes systems a little bit easier, means you have to multiply less numbers. Yes.
You just talked about reason for integrators. Is there something like that with time delays versus time advances in Z?
Exactly. There definitely is a reason for that. In Z domain, we like delays and not advances because in theory, we can't move forward in time. Right? Like imagine if we sent our first sample in and then we advance it by 1, like where's it going? Doesn't make sense. So we use delays a lot of times, and that's sort of the equivalent of 1/s's. Because it's z to the -1. Okay. Feel good? Okay, so let's divide everything by 3 just to make our denominator nice and pretty. That's gonna become y of s times s squared. I gave you the easy term. What's this next term? 2/3 s plus 2/3 equals 1/3 plus 1/3. Okay, we're still not in a form of 1/s's though. What are we gonna do?
Multiplication.
Yes, multiply both sides by 1/s squared. Very good. So we're gonna have y of s times 1. It's just 1 because s squared divided by s squared is 1 minus 2/3 1/s. That's an s. Plus 2/3 1/s squared. Okay, equals 1/3 1/s plus 1/3 1/s squared. X s. Okay.
One question.
Yes.
Why did this, never mind.
That is a good question, and I asked it quite a bit. Okay. Somebody asked a conceptual question about why we would we use direct form 2 over direct form 1. Is that a question a lot of us have?
Yeah.
Direct form 1, remember, you can do all your denominator stuff. I believe it's denominators. No,
Numerator.
numerator first and then denominator of 2. And it has 2 separate sets of integrators and mixers. Essentially, direct form 2 is nicer because you combine the integrators. It saves you on components. If you're actually going to build this in real life. Same thing actually with this denominator. By making it one, we cut down on the amount of gain stages we need just by having something be the same. Going out. You had a question, then we'll go back there.
I was just gonna say, I think Jeff's also mentioned in class that kind of a scam though. If you still need two integrators because you can't have two different inputs.
Yeah. It's also true. That's just one of the main reasons I think. If there was a different answer on the midterm, you could share that. But yes.
Yeah, so one over S is in duration, which is a time from like.
I believe so, yeah.
One over Z is a.
1 over Z is a time delay in like the discrete land. You can kind of see how 1 over S is analogous to Z -1. It's like an analogous, it's not the same thing, but in real life, we're doing a lot of discrete samples because computers are not perfect. They have to sample things with some level of discrete quantities. So that's ADCs and stuff. Yeah.
Did I say 1 minus 2/3, or is that 1 plus 2 over 3?
So this is 1 minus 2/3 times 1 over S. I wanted the 1 over S and the 1 over S squared to not be tied together in the denominator. Might have made it less clear, so I'm sorry about that. Okay. Feel good? Yes.
How do you build an integrator? Like, is that an op amp or?
Don't know.
240 textbook.
It's in the 240 textbook? 240? Okay, probably an op amp. Everything's op amp.
241, the practical electronics one.
So there's a way to build it. I don't know it. Sorry. Yes.
Okay, we might be getting to it, but I'm trying to remember. There was one where the form of it was like we had the derivatives. Like we had y, like and then y the first derivative, y the second derivative of y.
You think like the y double prime of t minus 3y prime of t equals say x prime of t, something like that.
Yes.
So this is like continuous time version. When we do a Laplace transforms, these derivatives, this is a nice property of the Laplace transform, and it's one of the reasons we use the Laplace transform is because it turns derivatives and integrals into algebra. Each of those derivatives become S's. Well, like this would be S for one derivative, S for another derivative, minus 3S for one of these derivatives. And of course, if you're doing it's the unilateral one with it has like the beginning cases where it gives you value of like y of 0 equals this. You would of course subtract those, but the essential property is that these S's are derivatives. So that's why 1 over S's are integrators. That makes sense. It's sort of the inverse of a derivative. Did that answer your question? I don't know if that was what you were looking for.
I think so, yes. So you're saying that just like those like derivatives become S's in the Laplace transform, and when you go back, they derivatives again. Oh.
Yep.
Okay, cool. Thank you.
Okay. We feel good?
Can you finish the diagram?
No. Yeah, okay. Fine. All right. Okay, we're gonna have arrows going through all of these, right? And they're gonna be coming back this way.
He's playing for a draw.
We're gonna have summers. Okay, I got lazy. It's not very boxy, and I used one summer symbol for a number. Now, are we gonna have all of these lines, ladies and gentlemen? Are all of these lines going to be there? No, why not? Only two terms in the numerator, that's right. You can think of this as, if you want to leave all these lines there, you can, it's just some of them, we're gonna multiply them by values of 0. Make sense?
Yep.
Yeah.
You mentioned that the denominator greatest term, you want it to be 1. And there was a conceptual thing about simplifying a real life circuit. What was that?
So the idea is if we make the denominator 1, that means we can always make the value of this term 1. Like normally, if that remained as a 3, we'd have to multiply it by 3 right there. That make sense?
Yeah, is there like a real world reason for that, or is it?
In reality, like you're gonna have to buy an op amp to change the value, right? Like you'd have to have an op amp with a gain of 3 in order to multiply it by 3. It's cheaper if you don't have one of those. Yeah.
Actually brings up a question I've had for a while. We want the gain of that top line to be 1, except aren't all the A coefficients negative? Why isn't it -1?
The short reason, the direction. You can kind of see how this is going toward the output. All of the other ones in the denominator are heading back in feedback towards the input. If they were in theory headed this way, then it'd be positive. That's a quick sort of shove the real answer under the rug that will get you the correct idea for the final. If you want the full theory of it, come talk to me later. I don't think we should talk about that right. Okay. So let's go through, add the numbers. Everyone, what's the value of the multiplier right here?
1.
1. Why is it 1?
That's
That's right. This is just f squared now. Great. What's the value of this one? 0. Why is it 0?
Nobody squared term makes it.
That's right. There was no s squared in the numerator slash. Now that we've made our numerator over here, there's no value that just has no 1 over s's attached to it. Okay, let's go down the numerator side. What's the value of this one? 1. Great. What about this one? No, sorry, that's 1/3. I believe.
Yes.
Yes. What's this one? I just trusted you guys.
So when is it?
Also, I included an extra integrator for no reason. So this is 0. Feel good about that. Do we see why I included too many integrators? Because I was dumb. Okay, let's go back down the denominator. What's the value of this one? 0, because there's too many integrators. Okay, what about this one?
-2.
It's 2/3 because this is 1 over s squared and it's negative y. Bend it back this way. That's the short answer. Just remember that one. Okay, what about this one? That is positive 2/3. Correct, because that is the opposite sign of what it was right there. You have done correct form 2. The 1 right here is positive because it's headed towards the output. That's short answer. Rushing things under the rug. It's better this way. Yes.
The discrete 10 case, I think it makes it simpler to think of all the coefficients coming directly from the recursive control. I don't know what that exactly looks like in continuous time because we have integrators. But yeah, you can think of the coefficients as something directly from the recursive form, which leads to all of the A coefficients except for A not having a negative.
Yes. That is great. And maybe I'll talk about it in my video. Recursive form, maybe of TDF2. Okay, I'll try and remember to talk about that. I have no idea who's next, so I'm just gonna go. You, yes.
I just had a quick question. So I know that by convention, the first one is always 1. Is it like technically incorrect if I wanted to keep 3 up there and then just have 2, -2, 1?
That would give you the same transfer function, yes.
Not the same.
It's not the same circuit if you were to build it, but it would do the same thing. That kind of makes sense. Okay, we'll go Jonathan, then we'll go there, and then Stefan. Okay,
Likely are we to need to know how to transpose this?
very unlikely. You guys remember the transpose?
Mental exercise.
Yep.
Yeah.
Yeah.
Don't worry about transpose. Is what I would recommend. If there's a transpose question on there, you can slap me 3 times.
Just get it wrong.
Yeah, just
Get it wrong.
get it wrong out of protest. That'll show him. Yeah.
If we all get it wrong, we all go to math.
Let's make a blood pact right now, everybody. Make 3.
Sorry, yeah?
I thought you related that S to
So how I related this, say how I went from this line to this line?
He was talking about like the S in general, how it's like a derivative.
Oh, yeah. So S is a derivative in Laplace land. And so a 1 over S is an integral. The same thing. It's an integrator. And because in real world derivative differentiators, they're called, introduce a lot of noise because of the slope of a line changes a lot due to noise. It's more effective to use integrator. So that's why we use 1 over S. Is that kind of what you're looking for? Did you want like algebra or? Okay, Stefan.
So would the numerator sides both be 1/3? So I'm kind of confused on which one corresponds.
Okay, let's say that this was 54. That one is now 54. 54 thirds. And that is 54 thirds as well. Which one of these is 54 thirds?
One.
Yes, why is it this one? 1. That's right. Well, it's 1 over S and not 1 over S squared, which means you would go through 2 integrators. Great. Any other questions on TDF2?
So the X ones, the numerator is always positive for everyone. It's only bottom on the left side.
Yep. So you leave the 1 as positive on the denominator and all the rest because they're going backwards or negatives. Maybe I can be clear in this video I'm now going to make about why that is. Okay. So this is TDF2. Y'all remember all the series and parallel stuff? Well, do you remember references to the diagrams that are serial in series and parallel?
Yeah.
So, yeah.
It'd be helpful if we could see you transform the transfer function into forms that are easier to find this series and direct diagrams for.
Okay. This is a good question. So, was it related? The same thing? Okay. Well, we'll do this first. I'm gonna do a quicker version that I'm gonna brush some stuff under the rug that I hope you guys remember how to do. Basically, if we want to find the series and parallel form of this, we should factor the bottom. That makes sense? Why we would do that? Because then we could split it up into a series of differential terms that are all multiplied by each other.
Fraction decom.
Yeah, well, we'll get there for the parallel form, but now we're still picking the series. This would be a form that looks kind of like S plus 2 over S minus or S plus 3 times S minus 2 times S plus 4. Right? And we can group these into individual series terms. And in theory, for each of those terms, you can build a form that looks just like this for each one of those, right? So let's build one for S plus 2 over S plus 3. Okay, how does this look? We have X of S coming in here, Y of S coming out here. We're gonna have a 1 over S right here. Right. There'll be a summer right there. Summer right there. Okay, what numbers do we put on the lines? What's this number?
1.
1. Why is it 1? That's this number right here. Okay, what is this number?
So one.
Also one, because this number is the coefficient in front of S. What's this number? Two. Why is it two?
It's just the numerator.
It's that one. This is the tricky one.
-3.
-3, correct, because it's this number, and because it's not the leading term, it's gonna be. Okay, now, because these are in series, it's the same thing as if we were to just go immediately from the output of this as the input to another block. That's doing this term. Does that make sense? Yeah.
And if it were in parallel, then you would have like basically two transfer functions added together.
Yeah, so you'd have like
Parallel.
x of s is coming in. And it would go into this function. And it would go into this function. It would go into this function. And then they'd all come out and be added after everything.
And then that literally just looks like two transfer functions being added together.
Exactly. 100%. So I feel like the series and parallel stuff felt a little intimidating. Just think, if you know how to do this, you know how to do this. Right? You just have to do this block and then do a small one. And then it's going to lead right into another block that looks like this one. And another block that looks like this one. And if they're parallel, let me just finish my thought and then I'll get to you. Now let's say instead it's something like 1 over s minus 2 plus s over s plus 5 minus 1 over, let's call this 2. 1 over 2s plus 3. What is this block like? We'll just repurpose this. What number's here? 1, because 1 right there. What number is here? 0. Why is it 0?
There's no S term on top of S.
No S term in the numerator. That's right. What is this number? 1, because that's 1 right there. What's this number? 2, because it's not the leading term in the denominator, so it's the negative of that number. Okay, we built that term. You can see that this is our input into that parallel function, and it's going to be added to the same input to this function. And so then we would just draw another block down here, doing the exact same things, same process, same filling out the numbers. Does that make sense? We feel pretty confident. When I said sweeping the factoring and partial fraction decomposition under the rug, do we feel confident with that? I feel like we had to do a ton of it. We feel fine? Okay. Yes, Jonathan.
So on that same homework, I think there's only 2 questions that ask this, but I'm still a little worried it might surprise us on the final. A block diagram with a feedback transfer function. That was done a little bit differently, and I don't quite remember what was different about that.
Okay. I think I remember that one. There's like a transfer function up this way, and then another transfer function down there, and it was like going an arrow like this. And you had to prove that they were equivalent to each other or something like that. Is that correct?
I think it was just write the transfer function in the Laplace domain I was asking for.
Okay. Can you email me that homework problem and I'll try and talk about it in this?
Video.
I really don't. You don't even know. I've done some TA review videos I TA'd for chem for a little bit. It was like I did a 3-hour video one time. It sucked.
I'll watch it.
You can subscribe to my YouTube channel. Yeah.
Maybe not here, but could like maybe talk about the domains.
Domains.
Yeah,
Okay.
domain
It's like domains and ranges, is that?
like
Yeah.
time domain.
Oh.
Domain, just
Like compare, contrast, characteristics.
Yeah. Yeah.
Okay.
Instant member subscription.
like sometimes I feel like sometimes I get lost.
Like seriously.
Time/frequency /Fourier. Fourier/DTFTs. Well, picture overview, maybe. Okay, yeah, I can do that. Yeah, send me that homework problem and I'll try and talk about it in there. What else? Technically, we only have the room for another 5 minutes, but I have no idea if there's anybody actually coming in, so.
Probably not.
Let's go Ryan first and then back to you, Jonathan.
Oh, are you asking like what topic or just any more questions?
Either, we can keep talking.
Okay. So if we did have time, if you just did a quick convolution refresh, I think that'd be it.
Oh, yeah, that might be nice. Convolution.
I mean, there's nothing quick about convolutions, but.
Yeah. Convolutions would be good. Yeah, Jonathan?
I still feel kind of iffy on understanding the differences between what were they called? Like infinite frequency response and limited frequency response.
Oh, like IIR, FIR?
Yeah. That'd be something I'd like to see on the video.
Okay. Y'all have to subscribe if you watch this whole thing.
You better turn on ads.
No, dude, I have to get like 10,000 views before I can monetize. Unfortunately. Is there a question over here? I thought I saw it. Oh, no, we're good. Okay, was there one back there? No, okay. I guess we'll do a convolution till whoever it is maybe kicks us out. Anybody can leave at any time, by the way, if you have other stuff to do. Of course. Thanks for stopping by, everybody. I'll send it out. But when I send out the video, it will be on my YouTube channel.
Oh, I gotta subscribe.
Thanks, Jack. Okay.
Plugging in your social like that.
That's right. Guys, I'm up to like 10 subscribers now. Pretty cool. Most of them are my immediate family.
Hey, if you post anything about 240,
I'm not
your views go crazy high.
Say again?
At 240.
I'm not.
Oh,
I made the video. It in.
What's your YouTube channel?
And
I think it's like Neil Switz or something. Is a fake name made up in second grade. I thought I was gonna need that.
Like a link to it somewhere?
I'll send out the YouTube video when I make it, and it will be on that channel. So you don't actually have to subscribe. Just for legal reasons. You only have to do it if you want to.
Also, we have the room the rest of the day.
Really?
No one has this. I just.
Wow.
Scheduler.
I guess just nobody wanted this room for some reason.
Well, you didn't want it either.
Well, that's fair.
Your last resort, so.
What? This was the only room they could find us in.
This isn't a bad room. It's not like it's not the Marb or
Yeah, I this isn't the worst room in the world.
Bro,
I agree with that.
80 in this room.
walls made out of blocks.
Like a tiny room.
Admittedly, I sat where there was like.
my wife does research up there, and
Everybody would have like.
So are you gonna like do practice?
I'm gonna do a convolution probably. Domain. That's the plan. And then
Is that recorded too?
I think so. As long as there's no problem with it. So.
No, it's one strong.
Great. Okay. Is everybody fine if we do graphical time domain convolution, then we call it?
For 3 hours.
We've been going, no, it's only been 2, right?
It's been 2 though. Do you want to take like a?
No. Well, we'll finish out. Yeah, Jonathan?
Only thing I'm iffy with time domain convolutions is if one side or the other is infinite and never goes back to 0.
Okay, so do we want to do one with like a step function?
Yes.
That sounds kind of fun, right?
Mm-hmm.
Okay.
So I'm doing.
Say we have a step function that starts at 2.
No. I got the.
You know what? Let's say it's magnitude 3. 'Cause that's a little spicy, isn't it?
A little spicy.
Fun. Okay. The formula for this is, I believe it's u of n minus 2.
Be 3 UN.
I won't be able to.
I'm sorry.
Yeah, I always get worried about getting the indices right, and then I come back later for the magnitude. It's a bad habit.
Are we doing straight then, or?
I think we're gonna do a continuous.
Okay.
Because I think most of the time, if you can kind of visualize doing a continuous, then it's easier to do a discrete.
Right.
Don't worry about boundaries, but that's about it.
Yeah.
For discrete method.
Any question, Jonathan?
Not really, just I guess pointing out that if we're doing continuous, you wrote n.
Oh, a fool. It's my bad, everybody. Okay, what do we want for our other function?
Right.
You want a triangle?
We'll make it a exponential function.
Invert it across the y-axis though.
Okay, but is that exponential gonna be on the test?
Well, wasn't it on the last?
Maybe it could be a half triangle, half exponential.
That's true.
Okay. I don't really want to do an exponential. I'm gonna do a triangle just because I think it gives you cooler insights. Okay, sorry. Kind of.
Look.
We're gonna put this triangle. Let's start it at 1.
Oh, it's
And
crazy.
it's gonna go to 2. Yeah, I'm not starting at the origin. We spicy like that. Magnitude, let's call it just goes to 1. That makes our life easier. Okay. Tell me, which of these is easier to flip, in my opinion? You have to know my opinion. You guys check that. The step. Why is it easier to flip the step, in my opinion? Again, psychics.
The limits of integration are really easy to model at just negative infinity. Yeah.
I think that's one idea. For me, if we flip this triangle, this is where I reveal the insights into my mind that you didn't figure out psychically for some reason. If we flip this, we're gonna have of some formula in terms of t minus tau. And then we have to find the formula for a line in terms of t minus tau as t shifts. And that's annoying, right? I don't enjoy doing that. But the step function, that's a constant value as long as we're in the right bounds. So that's why I like to flip flat functions if I can. Then it simplifies the formula. Does that make sense? Okay. If given a choice, flip a flat function over one of these. Okay, so we're gonna flip this. So let's just say that this is now the tau axis. Ooh, fun tau axis. And now we have our step function up here at magnitude 3. And this is, say this is x. And this is h. We're in tau now. So that one's h, this is x. Okay. So my question for y'all. This edge, where will it be in terms of t? Right? Like, this is the graph at t equals 0. Does that make sense?
Got it.
Yeah, we're doing t minus tau now. And so if t equals 0, we can see how the graph would be right here, right? And so if t was equal to 1, where would the graph be? Shifted 1 over this way. Make sense? Best is okay, very good. So what I like to do, this is a personal thing that I think helps clarify your integral bounds later, is I like to look at each edge and label where they are in terms of t. So right here is t in t equals 0, right? Anything that would be on the line would be at t. If t was 1, it would be over here. If t was -1, it would be right here. Does that kind of make sense? So this line will always be at the point of t minus 2. Does that kind of make sense? If t is equal to 1, this line will be at -1, which is 1 minus 2. If t equals 2, it will be at 0, which is 2 minus 2. Does that kind of make sense? Essentially, you take every edge in this shifting thing, you look at its index, and you add t to it. Yes, yeah, Jonathan, and then we'll go back to
If I recall correctly, you only label the edges of the moving function
moving one
in terms of t. The other ones remains at 1 and 2.
yeah, we'll talk about why I'm labeling edges of the moving function. It's useful, I promise. Yeah.
And so then when you're moving the rect function, it's always going to be in terms of t minus 2. And then you're always adding 1 to it when you move it over 1. Right, okay.
So like if t is equal to 1, then it's gonna be 1 minus 2, so this will be at -1.
Cool.
Exactly. So Now, what we're gonna think in terms of this convolution is when does an edge hit an edge? That's when things change in our convolutions, right? When things start overlapping or when they stop overlapping or when
Edge of the moving function and the edge.
the edge of the static function. So think we have our moving function and we have our static one. When does an edge of this one hit an edge of this one? So an edge like right here or right here. Does that make sense? Stefan, and then we'll go back there.
I was gonna get the answer.
Oh, okay. You were gonna do the same thing? We'll go with Stefan then.
T equals 3.
T equals 3. Why is it 3?
Because if we were to shift it over 3 by 3 times or by 1, 2, 3, then they'll hit. Yeah, cool.
That's right. That's when this edge hits this edge. So when T is less than 3, our convolution is equal to 0, right? Make sense? No overlap, no area, convolution is 0. At T is greater than 3, we start to have overlap. When does another edge hit an edge?
E equals 4.
Equals 4. Why 4?
When you cover it completely.
Yep, that's when this edge hits this edge. Right? So we're gonna do 4 right here. And I'll do equal signs here because they're gonna be equivalent at edges. Now, is there ever going to be a change after that? No, why not? No other edges are hitting other edges. No changes are happening between the two functions. Yeah.
So I might have missed this, but since it's a triangle, do we also want to one corner point at like the middle, the peak of the triangle, because it's kind of like two separate line functions. Does that make sense? What I'm trying to say?
It would if we came back down like this.
Right triangle.
Yeah, we're just a right triangle. You're good though. But no, that's an important insight. So think of an edge as when there's a change to your function. Right? Like we would have to write a different equation for that. That's like a big change happening. Okay, do we feel good with that? But we're gonna leave it as this right triangle because it's simple and fast. Okay, so we'll have one period when t is less than 3, one when it's between 3 and 4, and one where t is greater than 4. Okay, let's figure out our integrals. So the bounds of our integrals are, in my opinion, the hardest part of this idea. So we're thinking in terms of what's the bottom edge defining the overlap and what's the top edge defining our overlap. So from 3 to 4, this edge is moving through the triangle, right? It's moving progressively forward, and eventually it's going to hit right there at t equals 4. So what defines the lower edge of this overlap region? As that edge moves. It's 1. Why is it 1? Yeah, Ryan.
Because like for that triangle there, everything before 1 is 0. So 1 is gonna always be like that lowest cutoff.
Yes. And we're thinking 1 because we're integrating over tau.
Yeah.
That's what our convolution is in terms of, is tau. Like when we're done, we're only gonna have t's left, taus will be gone. So think about what value on the tau axis. Now, what about this upper edge? That's moving. That's kind of hard. How do we define that?
It's 2.
T minus 2. That's why I called it. I pointed it out right there. That's why it's nice to label edges. It's gonna be from 1 to t minus 2. Because as t is increasing, that's gonna define the upper edge, right? That t equals 3.5, our upper edge will be right in the middle. So that's where our integral should be. Make sense? Feel good about that? You feel good. You were giving me not feeling good about that vibes.
Why's the bottom 1 again?
The bottom is 1 because it's static on the 1 on the tick mark of 1 on the tau axis. Because the overlap right here on this non-moving function always stays right there. It's not in terms of t. It's not moving. It's always 1.
Are When we had defined our integration though, like this only is a thing when T starts at 3 and then ends at 4, so why isn't it the bottom?
Why isn't it 3? Good question. We're in D tau. So tau is equal to 1 for this function when t equals 3. T and tau are not the same. They use Greek versions of the same letters just to make it confusing. Don't let them win.
When you've graphed it here, you've graphed the x-axis as tau.
Yes, the axis is tau. We're in the tau domain. I get it. People like saying domain a lot. I get the confusion. Yes.
So now what would be on the inside of the integral with just the two equations?
That is it. That's correct. So on the inside of the equation, we're gonna have the equation for this one, which is, can anybody give it to me? What's the equation for that? 3. It's 3. That's nice. We can get rid of the step function because we put the step function in our bounds. That make sense? Okay, what's the formula for the other line though? A little bit harder.
T.
So it's going up to 1 at 2. It starts at 0.
It's just T.
It's
This one.
it's tau minus.
Sorry, tau minus.
You're good, but it makes sense why it's tau and not t, right? It's okay. It's okay. It's really easy to make these kind of mistakes. So why is it tau and not t? We're graphing the tau axis basically. This is a term and only in terms of tau. If it was moving, we'd have to define it in terms of t as well. And we wanted to specifically avoid that. So that's why we flipped the step function. Okay, so the inside of that is going to be tau minus 1. Do we all get where that formula came from? Makes sense. Slope is 1 and the y-intercept is -1. Okay. So that is an integral that we all could do, and it would give us the formula for the convolution between 3 and 4. And now at t is greater than or equal to 4, what are the bounds of our integral going to be? 2. Yes, it will be 1 from 1 to 2. Why is it from 1 to 2?
It's the only place where it's defined.
That's the only place where the overlap is, right? Because even though our step function is moving forever this way, like this triangle isn't defined past 2. So there will never be any overlap above it. And because it's infinite this way, there will be always overlap coming in. So it'll always just be from 1 to 2. Make sense? Very honest. I admire that. Yeah.
I guess one of the ways that it made sense to me when we were first learning this was like you could think about like doing another integral for just the step function, but it would just be times 0, right? Because there's just nothing there. And so like you can still do another one that is like 2 up to t minus 2, but it's just the integral of 3 times 0.
Exactly. You can think the edge of this step function is moving out here. And it's going farther and farther. But inside the integral, it would be 3 times 0 because this function is only defined right here. How does that feel? That's why our bounds are limited. That's why there are no t's in them. It's always just from 1 to 2. Okay, feel good? And what's inside the integral? Yep, it's the same thing. 3 times tau minus 1. And it's d tau. That would give us the formula for the convolution when t is greater than 4. And so if you do these integrals, you'll come out to either some constant value or some equation in terms of t. So if we were to graph this, we're going to get some graph, I believe, because this is a triangle hitting a square. We're going to get something that looks like a quadratic, and then it's going to cap off and go flat because the overlap is not increasing after the third point. Actually, this is not at 0. Sorry. This starts at 1, 2, 3. Like that. This is, okay, that's a really wide tick mark, but that's 3 to 4. Okay, not to scale.
Second, why do we have the T minus two at the upper bound?
At the upper bound, okay. So you remember how we defined this edge as T minus two? That's because as this is moving, as T is increasing and you're shifting it, that is defining the upper edge of the overlap. So as T is shifting from 3 to 4, thank you guys.
Thank you.
It defines the upper bound and it's moving, so it has to be some formula in terms of as T changes from 3 to 4. But once we get past 2, now it's not defining the upper edge of our overlap. This static point at 2 is. That's why the upper bound changes to 2. That kind of makes sense?
So the triangle's 2 is what the T minus 2 is for the step. Like
Yeah.
They're both their upper edges. The upper edge for the step is T minus 2, and the upper edge for the triangle is just 2.
That's right. And from 3 to 4, T minus 2 is limiting the overlap, and past 4, 2 is defining the overlap. Okay.
So I'm not asking you to do this for us, but I just have a sinking feeling that the final is going to have us do a convolution that requires piecewise integration.
Like multiple integrals?
That's kind of what we're doing here.
Well, yeah, but you were dividing it into regions, but there are some cases in which a single region have
Multiple overlaps.
yeah.
So that would be the case if we had something like this. Say your triangle comes back down. Then we're gonna have the same thing from 3 to 4. Does everybody see why we would have the same thing? But now at T is greater than 4, we're gonna have something different now. We're gonna still have this integral because this overlap will be the same thing. But now we have an overlap from 2 up to the edge of the step function as it's moving this way.
Also need to add an additional region.
So we're gonna have to do this integral plus another one from 2 to T minus 1. 2 is defining this lower edge of this overlap. And T minus 1 is defining this edge.
T minus 2.
Sorry, T minus 2. You're right.
I think there was like one.
My bad, everybody.
Baker. Why is it T minus 2?
T minus 2 because this is,
Oh, it's over 1. Or, oh, it's T minus.
it's still this edge as it's,
T minus 2 for the edges of the unit.
Yeah, okay. I was thinking it was T minus 1 to the.
exactly.
And then there'd be a fourth region for T is greater than.
What do you do? 5.
Greater than 5.
Yeah, assuming this is the same slope, so this is gonna hit at 3. But yeah, and so then there'd be another region out here with T is greater than 5. And it's gonna have this same integral again, plus this integral, but now the upper bound is 3 instead of T minus 2.
Would it be negative tau plus whatever the intersection at the y-axis is? I can't think.
I think it's like 3. Yeah, it'd be negative tau plus 3, so we'll have 3 times negative tau plus 3, I believe, is the formula for that.
Yeah, that would make sense, because then, yeah.
Yeah.
And then because these are nice shapes, like you could just find the area of that triangle and multiply it by the magnitude of the step function.
Yeah, for say like this constant one.
Yeah, or like the very last region where it's greater than, where T is greater than 5. Like it,
Oh, yeah, right here.
you could just
Like do that. Yep. I like to remember this one system because I'm lazy, but you can definitely do that, and that might be the easiest for you. How do we feel? We feel good about this? Any other details of this convolution to clarify?
Say about the last region that you didn't.
Oh, you want me to write this?
Talk about it maybe.
Okay.
Against.
So it's at T is greater than 5 because when T is greater than 5, T minus 2, this edge is past 3.
Yeah.
And so now the overlap for both of these sections is never changing.
Yeah.
So that's why it's greater than 5. And so we'll have the same overlap for the leftmost part of the triangle. So it'll be the same integral that we figured out before. minus one decal.
Still 1 to 2.
Still 1 to 2. Yep, because it's static, and then this integral is now from 2. And where it was t minus 2, because that edge was defining the upper part of our overlap, now it is 3. Because it's a static stop at 3. And again, the inside of our integral is 3 times negative tau plus 3 e tau. Okay, you feel good? Yeah, Sadie?
I was gonna say, hypothetically, that triangle, graph would probably be like this, and then like that, and then flatten out.
It would, so without this second triangle, I think it would be a quadratic going up, and then it would just hard stop. But now with the triangle going down, it is going to curve as if like a negative quadratic. You're right, yeah. That's my bet anyway, so. Okay. I think that is all I want to do today. Is that okay?
Thank you.
All right. Thank you, friend. I'll try and get this out soon. Is it scheduled?
Not anymore.
Not anymore.
Oh, that's convenient for y'all.
Yeah, there's still time.
I'm gonna take him though, because he has his.
Why are they still handles in this year of our Lord 2025?
No. That's a question for God, I suppose.
That is final.
Thank you, Prince.